In this video, we're going to discuss further anomaly detection concepts. We're going to build on some previous videos that we had where we discussed datasets, features, and unsupervised learning. The idea here is to detect anomalies. It's the weird stuff in data, things that we don't normally find in data. We want to detect those anomalies because it helps us to spot attacks that signatures and rules often miss. We're going to organize the discussion around three guiding ideas. First, distance. How far is something from the normal? Second, density. How crowded is the neighborhood? And third, reconstruction. Can we recreate this event from what we know about the normal events? By the end, you'll have both the vocabulary and models to understand anomaly detection at a practical level, at least the mental models anyway, within this lecture. That should be the outcome. Anomaly detection matters because attackers rarely look obviously malicious. They try to blend in. They mimic logins, borrow common tools, and hide in the noise of the normal data. Traditional defenses like signatures and static rules only catch what we already know about. They only catch the attacks that we're expecting and miss new tricks. Anomalies and anomaly detection, by contrast, are those small deviations from normal that we try to detect. They often serve as the very first sign that something's wrong. The real power of anomaly detection is that it can work even without labeled examples. It means that it's one of the most practical ways to stay ahead of constantly evolving threats. So what do we mean by normal? We keep using the word normal. Well, we mean the usual behavior of a person, a device, or a system over time. Think about your own life. When you wake up, you check your phone, you go to class or work, eat at certain times, and sleep. These patterns are what you would consider to be your normal pattern. Granted, we might be living in quite the chaotic world, and sometimes we don't have a normal that we can call an everyday normal, but we often do. Computers and users have patterns as well. Developers might be active at a certain time of day. Finance stuff might only work a couple hours a day. The finance staff within our organization, who knows what they do, but it probably doesn't take very long for them to do it. The important point is this: normal is relative. We don't judge one user against the entire company because we can't judge the amount of work that someone with an honest job would do compared to someone in HR. We wouldn't want to judge their behaviors and patterns against one another because they're going to be different. So we compare today's behavior, though, with past behavior or the same type for the same type of user or the same type of device. Before we build any detector, we have to choose what we're scoring. Are we looking at individual logins? Are we looking at 5-minute windows of activity per device? Are we looking at a single email message, maybe a process that starts on a laptop? That choice changes everything. If you only score simple single logins, you might miss a pattern that shows up after 10 logins in a row. If you score 5-minute windows, you'll see bursts, and then you'll see no activity, and maybe one event wouldn't show it. The key is clarity. You have to record your unit of analysis in one sentence. For example, we will score 5-minute windows per user for unusual login times and locations, meaning that if we don't count enough logins or login times attempts within that 5-minute window, then we don't consider it an anomaly. So you can see if we change that window to 10 minutes, then the number of failed logins might change. If we have it at 1 minute, the number of failed logins might be different. We might not detect something that's a slow-moving attack that attempts one single login every 90 seconds. Well, if we look at that, it's only going to detect 3 logins in any given 5-minute window. Maybe we have the opportunity, if it hits one more time, to get to 4 logins that are failed. But if that attacker is delaying things by random amounts between 90 and 120 seconds, we might never catch that if we choose a 5-minute window. So that choice shapes the patterns that we see and that we can then detect with whatever it is that we're attempting to detect for cybersecurity. Remember from a previous lecture, we talked about features, and features are just columns in that data set. They're measurable things that we use to describe behavior. For logins, A feature might be the hour of the day that the login attempt occurred, might be the city, geolocated city, might be the device type, or whether the login was successful or failed. For network traffic, features might be bytes sent, bytes received, duration, number of destinations contacted. All of those things are great features for network traffic. And when we combine them, good features tell a story. For example, bytes per minute tells us more than total bytes. New device or never seen before device tells us more than just a device ID. We want 5 or 10 clear columns that a non-technical teammate could understand when we're choosing those features. And to detect unusual events, we want a baseline of normal. That means picking a period of data that we believe is mostly ordinary. Maybe that's the last 2 weeks of normal work hours or a quiet overnight shift. It doesn't have to be perfect, but it needs to be free from obvious incidents. So if we had a port scan that occurred within that data, well, we might not want to include or choose that data. If we had a denial of service attack or something like that during that data, we might not want to choose that. We're looking for normal. We then use that baseline to describe what typical looks like. The key rule is to keep your baseline separate from the data that you're going to score. Don't accidentally teach the system that today's suspicious activity is part of the normal behavior. Features only work if they're on similar footing, if they look similar. Imagine comparing bytes sent, which might be in the millions, against failed logins, which might be in the single digits. Big numbers are going to dominate when we're training a model. To fix this, we put features on comparable scales. We talked about scaling of features in a previous video. So that might mean converting counts to rates or subtracting typical values and dividing by the typical spread, or using yes-no flags instead of just raw counts. You don't need to name the math exactly, just make sure that each feature has a fair chance in that decision. So it's important that signals aren't drowned out by big numbers when we're learning from the data that we have. Our first detector can be just simple. For each feature, look at its typical range during the baseline. Then check if the new value is far outside that range. If a user normally logs in between 7 a.m. and 6 p.m., a 2 a.m. login is far away from their normal time. If a device usually connects to 10 servers per hour but suddenly contacts 200, that's far away. Add up how unusual the features are and rank the events from the most unusual to the least unusual. You now have a basic anomaly detector with no complex math whatsoever, just comparisons using your intuition. And you can compare that to what's typical. But before you pick thresholds, start with people. How many alerts can your team actually look at in an hour without burning out? Maybe it's 10 during the day and 3 overnight. Maybe it's probably less than 3 overnight as someone who's been on call. But that's your alert budget. So you score a baseline day, rank events, and then pick the cutoff that doesn't give you too many alerts. If you flood analysts with too many alerts, then they're just going to start ignoring the alerts. And if you starve them with too few, you're going to miss important events. Always fit the system to the humans, not the other way around. The other idea is what's normal for one group might be strange for another. Admins often log in at 2 a.m. or sometimes log in at 2 a.m. Finance staff usually don't log in at 2 a.m. If we only compare everyone to the company-wide average, you'll drown in false positives. Instead, we should compare each user to themselves or to their peer group. That means building separate baselines for different groups with different roles. Or even keeping a personal baseline for each user. The goal is fairness. Judge each person or device by its own context. That neighborhood idea is also important here. Another way to think about anomalies is neighborhoods. Imagine all your events are dots on a map. Those dots are surrounded by lots of other dots. If they're surrounded by lots of other dots, that's probably normal. A dot off by itself, far from neighbors, is suspicious. We don't literally plot them in high dimensions, but the picture still helps. The question is this: does the event live in a crowded area or is it lonely? Lonely events deserve more attention. Some anomalies only make sense when you look at several events together. Single failed login may be nothing, but 10 failed logins followed by a success may point towards password guessing or brute force attack. One small data transfer could be harmless. A steady drip of small transfers every minute for hours may indicate data exfiltration. That's why we stress picking a unit of analysis earlier. Sequences matter. Use windows, time windows, and add features like counts in the last 15 minutes, the time since the last event, or maybe the number of unique destinations. Context also helps to sharpen detection. We can add features that capture the time of day, the day of week, or whether a device or domain has been seen before. Always remember to normalize those times. Pick a time zone and make sure time zones are normalized in the data that you are analyzing. Maybe you can add peer comparisons like deviation from the average for the same team. That context helps us to decide whether something is truly odd or just looks odd compared to the wrong baseline. Those context features help to reduce noise and improve trust in the system. There's a difference, of course, between rare and new. Rare means something happens seldom but has been seen before. Novel or new means it's never been seen at all. Both can be important. A port that only gets used once a month is rare, but if it's always used on the same server, that's expected. Maybe there's a monthly run of payroll or invoice payment or something like that. Brand new domain no one in the company has ever queried is novelty and maybe more suspicious. Features that capture both rarity and novelty can add strong signals to your detector. Missing values within data aren't just a nuisance, there can also be a signal. If a device suddenly stops reporting a field, that might be important. Instead of dropping the event, add a flag to say that the value is missing, and maybe we choose a clear default for that value. For example, if the city is missing, set it to unknown and keep a flag that says it's unknown. Treat missing values deliberately and intentionally so that the system stays honest and analysts know what's going on. Seasonality I talked about a little bit already, but patterns repeat in cycles. People behave differently on weekdays versus weekends. People behave differently during the day versus the night, and finance might be very active at the end of the quarter but quiet at other times. If you ignore those cycles, you'll mislabel normal as abnormal. The fix is simple. Build separate baselines for different slices of time. Compare Monday's logins to past Monday's logins, ignoring things like Labor Day or Memorial Day. Compare overnight to overnight. Always compare things with like. That's another variant of saying comparing apples to apples, which we talked about a little bit earlier as well. But sometimes normal reality will change. A company shifts to remote work, so the new tools roll out, or maybe cloud services are added. If the detector still uses last year's baseline, well, then it's going to raise constant false alarms. To prevent that, you want to refresh your baseline on a schedule, maybe monthly or quarterly, or after major changes. Keep a short note and record what each refresh looks like. So baseline was updated after cloud rollout would be a good way to describe something that occurred based on a cloud rollout. Why was the baseline updated? That way you know why your results change over time. And before rolling out an anomaly detector widely, you want to try it on a quiet day first. Test that detector on a calm day. Sort events by unusualness and read the top 20. Do they tell a story that makes sense? Can you explain each in one sentence? If not, well, then maybe choose different features, or maybe redo the baseline and try again. If most of the events are understandable and some are actually interesting, then you're on the right track. That simple test saves a lot of time and avoids frustration later. And avoid magic numbers within anomaly detection. You want to pick cutoffs that match a human workflow. One option is to take the top N per hour, the top number per hour or per day. Another is to require multiple unusual features before flagging something, so a scoring basis. Or maybe you can combine both. If you start with a normal baseline, a small baseline, and adjust weekly based on analyst feedback, then you're on the right track as well. The rule is to write down that rule in one clear sentence so anyone can understand and apply it. Deduplication is important as well. Multiple alerts for the same pattern are frustrating. You want to group similar items together. For example, combine 15 logins from the same user in a short time into one single case rather than 15 different cases. Combine dozens of flows from the same host into one fan-out case. That way, analysts will have fewer and clearer cases rather than floods of duplicates. That grouping increases trust and makes alerts actionable. Speaking of alerts, adding context to an alert is also very important. Alerts should explain themselves. Each one should answer why this, why now in plain language. Alerts should be actionable. For example, log in at 2:17 from a new city and a new device is far outside this user's pattern. You may want to look to make sure this user is not compromised in another way. Include key facts like the user's team, the device owner, other recent exceptions. If you have that context up front and there's no reason you can't provide that context up front, analysts can make faster and more confident decisions. Every detector should come with a short playbook. 3 checks that confirm or dismiss the alert quickly would be in a playbook, things that the analyst can check quickly and decide if they need to take the next step on that alert. For example, login anomalies. Step 1, check if the user was traveling. Step 2, check if the device is enrolled and is healthy. Then step 3, check if other users on the team showed similar behavior today. If 2 of the 3 checks reassure you, then you can close that ticket. If not, escalate it. Simple playbooks make responses faster and much more consistent. And we need to also learn from other analysts. A quick way for analysts to mark if an alert was useful or not useful with a one-line reason is gold at that point. And you can review those weekly. If many not useful alerts share a pattern, then maybe adjust features or adjust thresholds for your anomaly detector. If many useful alerts share a pattern, well, consider building a dedicated detector for that pattern. That feedback loop keeps the system aligned with real-world work instead of just drifting into noise and unactionable alerts. Anomaly detection often touches sensitive data, where people log in, what devices they use, what tools they run. As a security analyst, you want to respect that. Limit who can see sensitive fields. Log who looks at what. There's no reason that you can't log when someone accesses data, and that's very common in healthcare. Keep only fields that add real value and drop what doesn't. And explain the purpose of detection in plain language to your organization. Trust is an important part of security, and without it, tools will be resisted or worked around instead of embraced. So here's a simple pipeline for anomaly detection. Step 1, we want to ingest logs or flows. We've been working on that. Previous videos showed examples of that and exercises that we've had. How to ingest logs and what those look like. Step 2 is build a handful of clear behavior-focused features. And step 3, put those features on comparable scales. Step 4, compute that score. Score the unusualness of an event. And step 5, group similar events into one case. Step 6 is to add some context to our pipeline, to our events. And step 7 is to show only as many alerts as the humans can handle. And the final step is to capture feedback and adjust and refresh as needed. So we capture feedback on how well our pipeline is working, how well our anomaly detection is working, and then we adjust accordingly and refresh as needed. That's the full loop. Simple, repeatable, and explainable. Let's take a look at an example walkthrough of that pipeline. Let's use DNS first because everything is DNS, and DNS is everything. So if we have a unit, we choose a 5-minute window per device for DNS lookups. Features might include number of lookups, how many were brand new domains, average length of domain names, and how many came back with NX domain or no such domain. So the baseline is the last 2 weeks of daytime activity, and today we see a device suddenly asking for dozens of long random domains, most of them fail. Well, that would be unusual. That's an anomaly. So we group that into one case, and let's first check, is this a developer machine? Did new software just get installed for some reason? If not, then it's suspicious and worth digging into. Even if they installed new software, maybe it's suspicious and worth looking at closer. Another example, logins. Again, 5-minute window per user. Seems like a not unusual window of activity per user. Maybe some of the features we choose are what hour did this occur? Where did it occur from? What city? Is this a new device that they're signing in from? Was it successful? And successful, we want to, in that 5-minute window, include that as a rate. So how many within that 5-minute window occurred? Maybe the number of devices that they've tried within that 5-minute window. As a baseline, we use each user's last 2 weeks of logins. So what did they do over the last 2 weeks? Maybe we choose a month, maybe we choose 2 weeks, maybe we choose 1 week. But we want to try to capture as much activity as we can within a certain time frame, and a recent time frame as well. We already discussed that. So today we see a login at 2:17 again. Maybe it's from a new city on a new device, and there are several failures. Well, that would be unusual. So again, we would put all of those logins into one case and provide some context for maybe the travel history if we know the user is traveling or something like that. If we have that information, often we might not. But is the device something that we've ever seen before? If not, then we want to escalate that because maybe that user's account just got broken into through a brute force attack. Another example, final example that we'll look at is endpoints. If we're looking at an endpoint, maybe we look at the process starts, the number of processes that have happened, number of new processes that have been kicked off by an endpoint within the last 5 minutes or whatever window of time we choose. Maybe some of the features that we choose include parent-child program pairs. Is another program starting or spawning other processes on that machine? Whether we've ever seen that parent-child program pair, or we've seen, let's say, Word kick off scripting, that can happen. Microsoft Word can kick off scripts or Excel or something like that. But have we ever seen that happen for this user? Whether it touched the network, did it reach out to the network? Did it try to perform other sensitive actions like installing other software? Was it trying to escalate itself on that same machine? So the baseline, again, maybe we choose 2 weeks for that type of host, for that type of role within the company. And now today, let's say we see a document reader. Adobe is trying to spawn a script engine, which then tries to kick off a network tool of some kind, a wget or something to retrieve some other information. That's something that would be quite unusual. Again, bundle that into one case and check to see maybe a software update was running. That could explain it. Otherwise, it's worth an investigation. So those examples are some anomalous activity that we might want to look at. And the common things, if we think about those, are some time windows and establishing baselines. What's normal behavior for that machine or that user? And then trying to figure out if it's an anomaly based on what that person is doing. Complicated metrics aren't necessarily needed, at least right now. We just want to measure 3 things in plain language. Of the alerts that we raised this week, how many did we find useful? How many did we catch of incidents this week that were first flagged by our anomaly detection? And how long after that unusual behavior started did we raise an alert? Those answers will tell us if the system helps. If it's improving maybe, or we're early days in implementation, we might still need to be improving this system, but it'll tell us if we're going in the right direction. And when we're working with anomaly detection, the detectors age. Roles change, people move within the company, software changes, networks change. If we have two maintenance tasks, first monthly tuning, reviewing alerts that aren't useful and adjusting our features that we choose, adjusting our grouping or our thresholds, our time window, those types of things. Maybe we do that monthly. We might probably do that more often at first, but we make sure to set some time aside to do that monthly. Second, quarterly refreshes. So rebuild that baseline maybe quarterly for our recent data. Then we can grab a new baseline from there. And again, remember to keep track of why you're updating that baseline or when you're updating that baseline. Maybe you rolled out a new VPN or something like that. Anything that has significantly different patterns, you're going to recapture that baseline, but record why you're doing it, because you won't remember a month from now even why you might have updated that baseline. Things move very quickly, and we're not slowing down at any point now. So common pitfalls that happen with anomaly detection, we might be comparing apples to oranges. So an admin versus a new hire is going to have significantly different patterns of behavior. We want to make sure to compare people to themselves or to peers within that same group. Another pitfall is drowning in alerts. We just have too many alerts and they're not actionable, and we're getting alerts at all times for things that we just don't care about. I once worked at a company where you would get an alert at 2 a.m. every night when a job finished, an overnight job. And I asked why, and they said, well, because you just want to know that it finished. And I said, I don't want to know when it finishes. I want to know when it doesn't finish. So if it gets to be 3 o'clock in the morning and it's not done yet, then maybe send the alert. But even then, I couldn't do anything about it until morning. So there's no reason to send that alert. I didn't win that argument, but regardless, it points out the problem. Too many alerts, and you just end up turning off the phone and not paying attention to it. One of the other pitfalls is to treat missing data purposefully. So don't ignore missing data. Mark it missing on purpose. Mark it missing and say, this was missing. Or set a flag saying, this field is missing, yes, no. Another pitfall, baselines becoming stale. Making sure you refresh on a schedule will definitely help as to keeping up with that anomaly detection. So in this lecture, we built some foundation around anomaly detection in plain language. We defined what normal means, picked clear units of analysis, chose features that help tell a story. We talked about all of those things here in this lecture, and talked about scoring unusualness, grouping alerts, setting alert budgets, and so on. And we're going to add to this with some actual named models, and we're going to introduce each and hopefully ways that'll help you connect the dots from where we've been to where we're going and build some scaffolding that we already have, continue to build that scaffolding that we already have here from previous videos. All right. Thank you for watching.